Good afternoon to all. So I think we have on the verge of completion of the unit number 6, that is steam condensers. Still will little bit revise things, and one article is required, that is mass of cooling water required. That will take, and we'll go to the next topic. So steam condenser, we'll define steam condenser. So steam condenser is a device in which steam is condensed to water at a pressure less than atmospheric, that is vacuum. Condensation can be done by removing heat from exhaust steam using circulating cooling water. So cooling water we're using to cool that particular steam. And during condensation, working substance changes its phase from vapor to liquid. So exhaust steam is in vapor form, and after condensation it is converted into liquid and rejects latent heat. So only it is rejecting the latent heat. The exhaust pressure in the condenser is maintained. This general suggestion, that is maintained nearly about 7 to 8 kilopascal. 7 to 8 kilopascal means 0.07 bar or 0.08 bar if you convert into bar, which correspond to condensed temperature. Okay, sorry for the because internet connection was lost here. Am I audible clearly now? Somebody can reply.
Yes, sir.
Okay. Is screen visible? So functions of condenser is to reduce the turbine pressure, and we know that as EPC turbine condenser pressure is inversely proportional to Rankine cycle efficiency, and if condenser pressure is too much low, then definitely efficiency will be more. And to condense it exhaust steam from the turbine and pure water, whatever the condenser is there, it is converting that steam into the pure water, pure feed water, and that can be reused into the boiler, and it is a pure feed water, therefore require require less or it compensates some losses. Or water treatment is in case of the surface condensers, water treatment is not required. Enables removal of air and other non-conductive gases from steam with the help of that external pump. And then elements of condensing plant we have discussed a lot. So this is a cooling tower. Whenever the amount of water, when we have to use cooling tower, anybody of you, when we have to use cooling tower, when cooling tower should not be used, or it is not expected to use the cooling tower. Anybody of you? So when water is less good, when water quantity very good, when water quantity limited water supply is there, then we have to reuse the water again and again. Then we have to use the cooling tower. Then this cooling tower cools the cooling water, okay, which is heated from the condenser as it has taken the heat. The cooling water pump here it extracts the water from the cooling tower, then it is supplied to the condenser. So whatever the heat is there of the steam is absorbed by the cooling water, and this water get heated again, it is cooled again, and it is used once again. So this is whatever the water is evaporated from the cooling tower, it is it is supplied as a makeup water from the river or another source. And then this condensate, as pressure inside the condenser is vacuum less than atmospheric pressure, this water that condensate will not come directly to the hot well, therefore condensate extraction pumps we are using. Okay, and now afterwards we learned that some of the condenser, that is high level jet condenser, this condensate extraction pump is not required. So hot well is there where we are storing the condensate, it is reused as a feed water to the boiler. Then we want a vacuum inside the condenser, therefore whatever the air is entering to the into the condenser, maybe from the steam, maybe from the water, is going to be we have to remove the air continuously with the help of air extraction pump. So this with the help of this air extraction pump, so we are removing the air continuously. So this is the elements of condensing plant. In classification of condensers, we are having two types of condensers. One is jet condenser and another is what? They are surface condenser. So jet condenser means low level jet condenser, low level counter flow. Low level counter flow is there. Then low level parallel flow, high level jet condenser and ejector jet condenser. So according to direction, this parallel flow, both steam and that cooling water is there. If they are flowing in the same direction, then it is any type of condenser is parallel flow. Counter flow, if cooling water and steam, exhaust steam, they are flowing in the opposite direction, then they are will be counter flow. Cross flow means exactly they are going to be cross. One is cooling water is perpendicular, cooling water pipeline is perpendicular to the exhaust steam pipeline. So this is a cross flow type of thing. Okay, so we discussed one by one. Jet condenser, anybody of you? Now I want a little bit revision from your side. Jet condenser means anybody? Because MCQ they are going to ask these questions. Jet condenser means nobody is replying. Very simple. Jet condenser means the condenser in which jet condenser. How we define jet? Now we define surface. Anybody can unmute and tell, or chat box is open. Maybe somebody may be typing. Instead of, so jet condenser means the condenser in which water, cooling water and that exhaust steam directly get mixed with each other. So that is a jet condenser. And surface condenser, they doesn't mix with each other. They may flow in the pipeline or tubes, in the form of tubes. Okay, so there are surface condenser, shell and tube, depending on the direction of steam, down flow, center flow, inverted flow. Okay, and you have two type of condenser where limited source of water is available. So this we have discussed. Jet condenser, exhaust steam and cooling water are direct in contact, mix with each other. Final temperature of condenser and cooling water leaving the condenser is same. The jet condenser is very simple in design, cheaper. It can be used when cooling water is cheap and easily available. Condensate cannot be used in boiler because it is mixed with the cooling water. So this is a cooling exhaust steam. So that direction diagram, another diagram I have taken. So vacuum created is up to 6 kilopascal, so 0.06 kilopascal. So exhaust steam is flowing. So parallel flow, exhaust steam is flowing in this direction. So and yeah, this is a cooling water is flowing from maybe what here one cooling river, cooling pond. This is circulated. Both are flowing in the downward direction. Cooling water and this air steam, and definitely condensate is mixed, they are mixed with, and condensate air and coolant they are taken at the bottom side. Then low level counterflow. So this is a counterflow type of it. Condenser cooling water is supplied here, air extraction to 5.5 meter height, low level 10.363 means high levels. Okay, so we have discussed a lot. Then high level jet condenser, this is tailpipe height is much more. It is 10.33 meter column height is there. Okay. And the baffles are there. Cooling water is flowing from the top to bottom. Exhaust steam is flowing from the bottom to top. Here counter flow is there. And in this case, the mix gear, they are get mixed with each other, and tailpipe height is more. Water is clearly coming to the hot wheel without any kind of pump. But as this height is much more, that cooling pound to this here, cooling pound to this condenser, therefore circulation pump, here circulating pump is required, but here extraction pump is not, condensate extraction pump is not required. So that we have discussed. Ejector condenser, convergent divergent nozzles are used. So convergent nozzles will increase the velocity of that particular exhaust steam and cooling water. Due to, because of that, here the cooling water and exhaust steam are effectively mixed with each other. And at the divergent side, what is there? So divergent side, here velocity is decreasing and pressure is increasing. As pressure is becoming too much more than atmospheric pressure, the condensate is directly coming with the help of that pressure, because divergence section velocity were increasing and we are velocity were decreasing and we are increasing the pressure. And when pressure will become much more than atmospheric pressure, then this condensate and cooling tower will come down naturally. Okay, so this is the ejector type of condenser. Momentum of flowing water is used to remove a mixture of condensate and cooling water from condenser without use of any extraction pump. So momentum is a divergent section, pressure is increased. Then advantages, simple in jet, simple, less floor area, condensate is pure, not pure, cannot use, low vacuum efficiency, and surface condensers. So these are the shell and tube type of surface condenser. Figures may be a little bit different because this PPT I got yesterday, having some explanation. I'm uploading on our WhatsApp group today only. So in surface condenser, the exhaust steam and cooling water do not mix physically. So they are flowing in the pipeline. So cooling water is flowing in the pipeline, and around them the steam is flowing. And when steam here, there is a passes of the cooling water. Then there is shell is there. This cooling water will exhaust steam, cooling water and exhaust steam heat transfer will take place. So whatever the heat is there of the steam is only absorbed by the cooling water and it is get heated, and this is cooling water in. So cooling water out is having more temperature, cooling water in definitely it is having less temperature, because it will absorb the heat and its temperature will increase. Then here, depending on this direction, downflow, the exhaust stream is flowing in the downward direction, and here exhaust stream enter the top of the condenser shell and flow downward. Okay, then it is called as downflow condenser. Water tubes are double passed. The cold water flows in lower side first and then in upper side. So water steam is flowing in the downward direction, and condensate action pump is located at the bottom side. So this is the downflow. Central flow means what? Steam flows radially in here in this direction. The central air extraction pump is located at the center. Okay, and the steam get access to the entire periphery of the tubes. The steam ला सगळ्या periphery पासून access मिळतो. And this large surface area for heat transfer is available as compared to the downflow. So radial flow is little bit more effective than the air center downflow. In inverter flow, the steam enter at the bottom of the shell and air extraction pump connected at the top. उलट केलेलं आहे यामध्ये. The steam flows upward first and subsequently returns to the bottom of the condenser. The condensation pump is connected at the bottom. Okay, so you have primitive type of condenser, where now you have primitive type means what? Inside these, up till now, whatever the surface condensers are there, inside that cooling water is flowing inside the tubes. But in this evaporative type of condenser, the evaporation of cooling water provides the cooling effect. Steam is to be condensed, is passed through the grilled pipe. As in the pipes only, the steam is flowing inside the grilled pipes. Okay, and here water, the cooling water is going to be, so we are passing around this particular here, passing from over this particular yield tubes. So these are the small nozzles are there. So these nozzles were from this here sump or reservoir or sump is there. So from this pump, with the help of pump, this cooling water is going to be supplied to the nozzles. Nozzles breaks this minute particles and sprayed over this particular gill tubes. So these gill tubes will evaporate what are the heat required for the evaporation. It will take from the steam. Steam is get condensed, and this condensation can be removed here. And this pump cooling water, while flowing inside the direction, it is coming in contact with air. Okay, and air will pull that particular cooling water and again recirculated back. So some whatever water is getting evaporated, it is supplied in the form of makeup water. So this is a evaporative type of condenser, more suitable for small plants where supply of cold water is limited. So that also I have explained. The advantage and surface condenser: high vacuum efficiency, pure condensate, make no mixing of cooling water, and that low quality of cooling water can be used because it is not mixed with the steam. Therefore, we can use it. Allows the expansion of steam through a higher pressure ratio. As vacuum is more, so higher pressure ratio can be obtained, that is boiler pressure to condenser pressure. Then large amount of water is required. The construction is complicated, costly maintenance and skilled workers are required. Larger floor space because it is indirect mixing, and this difference also we have worked for. In this effect of rank condenser pressure on we have discussed lowering the condenser pressure will increase the area influenced by the cycle on TS diagram, which indicate that net work will increase. The thermal efficiency. So here we know that this diagram I have confirmed. So if the condenser pressure is decreased, point number 4 will shift from 4 to 4 dash. Okay, and here condenser pressure, this is a P4 dash. This is condenser pressure increased, decreased the condenser pressure is P4 dash, and P4 is the here initial condenser pressure. So definitely for 4 dash, 1 will shift to 1 dash, 2 will shift to 2 dash. Network obtained area will be increasing. So this much amount of hatching, this much amount of work is will increase here with due to the decrease in condenser pressure. So therefore, instead of going for the atmospheric pressure, here we are going that we are expect that we should use vacuum pressure inside the condenser is less than the atmospheric pressure, so that total plant efficiency, thermal efficiency of the plant will get increased. In vacuum creation, so vacuum creation means it is a In steam condensation in cold vessel, the vapor phase of our conception change to liquid phase, and the specific volume reduces to more than 1000 times. So due to change in air volume, so minimum pressure obtained, that is air. Vacuum is vacuum creation, atmospheric pressure minus vacuum gauge pressure. So less than atmospheric pressure is called as vacuum, and it is generated by the help of air pump. So we have to remove the air from the condenser, and if air is get removed, definitely there will be vacuum. No air means vacuum. Then sources of air inside the condenser, how the air is going to be entering into the condenser. So ambient air leaks to the condenser chamber at the joints. I told you joints, glands, which are internally under pressure or lower than the ambient. So joints and leakages may happen. Another source of air is dissolved air water with feed water. Okay, then with the steam and effect of air pressure, the pressure it will increases the pressure and destroy the vacuum. Air has a poor thermal conductivity, hence the rate of heat transfer from vapor to cooling medium is reduced, and presence of air in the condenser corrodes the metal. So corrosion will occur. So these are the effects of air leakage. So this is, I think we have discussed about this. Then here one more article is there. Okay, cooling water and steamer may get okay. So anybody having doubt up till now? I am taking revision because it is a very important chapter as far as the MCQs are concerned, and therefore one stroke revision I am going for. So instead of going for a little revision after a long time, no doubt, sir. Asmita, thank you. Others, please reply. Asmita, no doubt. Others. Please, no one, no doubt. Others, please reply. Now, one article is remained here from this here. Here, mass of cooling water required. Return. Mass of cooling water required. Mass of cooling water required for condensation. How much amount of cooling water is required to air condense the steam? So that we have to mass of cooling water required. Okay, now here we are considering one condenser. Let us consider one condenser. Let us consider that ms amount of steam, mass of steam is ms, and its enthalpy having enthalpy hs. is supplied to the condenser. Let us this steam is going to be supplied. Okay. And this MW amount of water is circulating, okay, for the condensation of this ms amount of steam and having temperature TW1. Let us consider the cooling water temperature is TW1, having temperature TW1 is circulated in this, okay, and here MW will become same mass of water. Cooling water will assume that there is no evaporation and temperature of this will be TW2. What happens in this particular condenser? Maybe it may be jet condenser if you consider the heat balance. So how we can write one equation, that is, anybody of you? So what are the heat? Who is losing the heat? Anybody? Who is losing the heat? And definitely the steam will condensate will be having mass will be definitely it will be equal to ms or mc, and here condensate will be hc will be the enthalpy of condensate because it will convert into condensate. Okay, so how much amount of who is losing the heat and who is gaining the heat? Anybody of you? So if you consider the pure form, anybody of you who is gaining the heat? So we have to write with the help of heat balance equation. So by heat balance equation means what? What heat is going to be balanced? Heat by heat balance equation or heat balance. By heat balance. Anybody? I can write one heat balance equation. Anybody of you? Who is gaining the heat and who is losing the heat? Anybody of you? So heat will be lost by steam. So heat lost by steam. Steam is losing the heat because it is cooling, exhausting steam. Heat lost by steam. Heat lost by steam is equal to what will be? Who is getting the heat? Heat gained by it will be gained by cooling water. So cooling water will gain the heat. And then steam will lost by heat lost by steam is equal to heat gained by cooling water. So this is the equation, and from this we have to calculate the mass of water required. Heat gained by water. Okay. So therefore, what we can write here, heat lost by steam. How much steam will lose the heat? So it is equal to ms amount of heat is ms amount of mass. So it is having initially enthalpy how much? Hs. So Hs okay minus Hw. Condensate enthalpy will be Hs Hc. Okay. So is equal to heat gained by water. What is the heat gained by water? So mass of water will be mw. Let us consider CPW is a specific heat at constant pressure of cooling water. It's mw. CPW. Into bracket TW2 positive difference minus TW1. Okay, so this is the equation. So MW MS is equal to MS. So generally the whatever the steam, so if you observe the Rankine cycle here, whatever the steam is flowing into the Rankine cycle here, condenser entering into the condenser, it is at point number 2, and generally this steam is always what? Wet steam. This is always wet steam. Therefore HS we can write as a HF plus X into HFG. So therefore we can write this equation as a MS into bracket HF plus X into HFG minus HC is equal to MW into CPW into bracket TW2 okay, and this will be the mass of cooling water required. So MW upon MS. So if you want this cooling ratio, okay, cooling ratio or cooling water quantity MW upon MS, if you want, it is called as cooling ratio and is equal to now MW upon MS. Up till now understood? Please mention in chat box or please reply. Anybody having objection, doubt, please reply. Up till now understood? Please reply. Prerna, Smita, or whether screen was visible, I don't know. I have to repeat. Visible. Now, was the screen visible, Asmita? Was screen visible, or now it is visible? Was the screen visible? Because I'm visible. Okay. Now you understood everything. Okay. So this much is the cooling ratio. So yes, sir. Okay. Thank you. So now we want cooling ratio. So MW upon MS, we want how much amount of cooling water we require. So in that case, MW upon MS is equal to MW amount of cooling water required. How much is required? MW upon MS is called as cooling ratio and is equal to, how it is equal to, is equal to here HS HF HF plus X into HFG minus HC divided by CPW into bracket TW2 minus TW1. This is the amount of cooling water required. So HF F plus XHFG minus HC. It depends on pressure also. The dry aspect of that particular steam. Mass air enthalpy of steam means temperature of that particular condensate, and CPW. Generally 50 to 60 for means condensing 1 kg of steam. Generally 50 to 60 kg of water is required, or 50 to 60 liter of water is required. This is general observation. It's called as cooling ratio. Understood? So please write this. I will circulate the notes also. Class notes I will circulate. So understood by everybody? Please mention. Yes, sir, understood. Asmita only replying. Prerna and Asmita. Others please reply. I think 30 students are in class, but only 2 are replying. Please reply. Write down also. HC means enthalpy of condensate, MW mass of cooling water, CPW is because it is more, water will not change its phase. Therefore, it will remain only, it will absorb sensible heat, and this will absorb latent. This will give the latent heat. You see, one is losing the phase, a vapor to liquid, but one water phase will not be. It is in only one phase, and it is sensible. Please reply. So this chapter is not having any kind of numericals, so definitely numericals will not be there for any kind of chapter now because it's online test over. Okay. So we'll revise what two efficiency once again so that we'll close this chapter. I will request you to join once again because now today we have completed the chapter. We have to enter into the new chapter and new recording we have to go for. Therefore, enter. I will provide once again one link. So with that link, you join. It's the one. Okay. So once again, two efficiencies are there related to the condenser. Anybody of you can define. Sorry. Thank you, Prerna. So we have defined vacuum efficiency where we want to define. So we know that due to some amount of air leaks into the condenser, the actual vacuum present inside the condenser is lower than the ideal vacuum. Okay, and therefore ideal vacuum or highest vacuum is corresponding to the saturation pressure of here saturation pressure at which the phase conversion occurs, that is vapor to liquid. So that will be the occurs saturation pressure. Will consider, let us consider PS at which is condenser pressure. Now we are denoting it by PC, PS. Okay, condenser pressure. So therefore PS actual barometric atmospheric pressure minus PS means saturation air is the maximum possible vacuum inside the condenser. So PB means barometric. So vacuum is always lesser than the atmospheric pressure. So it is always should be subtracted from atmospheric pressure. So PB minus PS is the ideal vacuum or maximum possible vacuum inside the condenser, and total, but actually we know that actual conditions is barometric pressure will be PB, no doubt. Total condenser pressure will be PA because some of air will be present inside the condenser, and therefore the total pressure will be, condenser pressure will be partial pressure exerted by air. It is by Dalton's law. One law is there. So it is a Dalton's law telling that total pressure inside the condenser is equal to partial pressure of air plus partial pressure of here steam. Okay, therefore PA plus PS is equal to PT, and due to this air pressure vacuum, this much difference is much more, and therefore PB minus PT will be decreasing. So PB minus PT is the actual vacuum, and which is with air, whatever the air is present inside the condenser, which is less pressure. And this ratio definition, vacuum efficiency, now ratio of actual vacuum inside the condenser to the ideal vacuum inside the condenser is called as vacuum efficiency. That is PB minus PT. Okay, PT is partial pressure of sum of partial pressure of air and sum of partial pressure of steam, and PB minus PT divided by PB minus PS. This is a maximum or ideal pressure, ideal vacuum. It is corresponding to saturation pressure of steam. So this ratio, it is actual vacuum PB minus PT divided by PB minus PM, ideal vacuum or maximum possible vacuum, is called as vacuum efficiency of the condenser. So thus there is no air leakage. Air leakage or shelter. If there is no air leakage, then vacuum efficiency will be 100%. Vacuum efficiency depending on the barometric pressure also. Increase in barometric pressure causes reduction in vacuum efficiency. If cooling water is insufficient pressure inside the condenser increase, and thus reduces the vacuum. Now another efficiency is condenser efficiency. So many definitions are there for condenser efficiency. So actual rise in temperature of cooling water to maximum possible rise in temperature of cooling water. So TW outlet minus TW or TW2 minus TW1 divided by TS. So on that day I have one for one graph length of the condenser. Okay, let us, this will be latent heat, therefore temperature will remain constant. That we are assuming it as a TS. Okay, and actual rise in condenser, let us consider this as a counter flow heat exchanger, counter flow condenser. So let us, TW1 is the inlet temperature, and while it is going, TW2 will be the temperature will increase. So actual rise in the cooling water temperature is what? TW2 minus TW1, but they are given T cooling water outlet, that is we are denoting by TW2 minus TW1. Okay, and this is the temperature of steam. Maximum how much will rise will take place? एवढी झाली, पण मॅक्झिमम एवढी घ्यायला पाहिजे किती? TS minus TW1. TS here आपल्याला आपण म्हटलं तर TS, okay, आपलं symbol is that day minus TW1. So this will be the here maximum possible rise. So this actual rise in cooling water temperature divided by maximum possible rise in cooling water temperature is called as condenser efficiency. And you know the cooling towers, used to reducing the temperature. So this is the definition of condensed efficiency and vacuum efficiency. Everybody understand? Please reply. That day I have covered it little bit fast within 10 minutes. Therefore, I revised. I thought that okay, instead of going for completion of syllabus early, we'll go slowly. Understood, sir? Okay. Understood. Okay. Thank you. Others, please reply so that we'll close the chapter. I have to upload these 2 PPT slides are there to on your WhatsApp group. Understood, Prerna? Others, please reply. Girls replying, boys reply. And little bit some PPTs are also there. Will revise. Cooling tower, I don't know. You use it for reducing the temperature of hot cooling water. Hot cooling water. Hot cooling water rejects it to atmospheric air. Cooling water uses principle of evaporative cooling. So amount evaporative cooling means whatever the evaporation, whatever the heat is required, latent heat is required for that water, it will take from the steam and it will get evaporated. So thermodynamic analysis, I have only now one for heat lost by steam is equal to heat gained by cooling water. So amount of heat required. So MS H steam minus H condensate is equal to MWCPW into TWO We have nomenclature. MS into bracket HF1 plus X1 HFG1 minus H condensate is equal to MWCP2 TW. Okay, and this will be MW upon MS will be the cooling ratio. So this is a cooling tower. So cooling tower air at here it will be, we want to cool the cooling water from the cooling which is coming from the condenser, and this condenser condensate because it is get heated and we want to reuse that water. So for what we are doing is hot water from condenser is entering into the top here, okay, and air is flowing through this particular air layers are there. So cooling towers are the big construction. It may be made up of steel, or sometimes it is made up of some construction material like bricks, etc. So from the top, the cooling hot water is going to be sprayed, and air is entering into the top direction. Okay, and air to atmosphere. Now it is a forced draft cooling tower is there. So this is the blower. Induced draft fans are used. So these fans will pull the air into the in upward direction, and due to that, air speed is increasing. And if air speed is increasing, water cooling rate will become faster and faster. So this is air in. So air is entering into this direction from bottom direction. Here water is entering, spraying into the top direction. Air is here removed means to the upward direction with the force. Therefore, just वारा असेल तर दिल्ली this काय होणार this पाणी लवकर गारणार. So because of the forced cooling, okay, and this cooling water is get cooled, and this cooling water is again reused into the water pump to condenser. So this is the condenser to cooling water. So make a water pump is there. So this is the cooling tower construction. It is a big, huge building. Height is much more. Okay. So if you are going to the condenser, some kind of steam power plants, okay, nearby that the top buildings are there. So one of them is the chimney is there, and another this kind of construction is there. It is going to be cooling tower. Generally, hyperbolic type construction is there. So this is like this. Because why? It actually a construction as hyperbolic type. Here you see the square picture. And why? Because if air is flowing in this direction, so at the as area available for the flow is decreasing, velocity will increase. And so to increase the kinetic energy, velocity of that particular air, we are using this kind of hyperbolic cooling tower. So the construction is like a hyperbolic. So at the bottom, the space width is much more, at the top width is less. So eliminators are there, and this will be the cooling tower. So cooling tower was, I think, eliminated from our syllabus, but still. So rate of cooling tower depends on amount of water at surface exposed to air, time of exposure, humidity, direction of flow of water and air. So natural draft means what? Only change is their natural draft cooling tower. There is no fans used. If these fans are not used, then it is called as natural draft. With only air is going to be circulated naturally in upward direction, like this hyperbolic type construction. And so this is a natural draft cooling tower. Do not require fan for air movement. Also called hyperbolic cooling tower. Construction is like this. Okay, hyperbolic. Okay, and very big in size compared to towers using fan. So this completes our chapter condenser. Okay. So anybody having doubt? Understand last part, tower, etc. Also I have discussed it. Okay. So understood. Understood or not? Shall I conclude this chapter? Yes, sir. Yes, sir. Understood. SA11. Okay. So, okay. Smith understanding. Okay. So, shall I conclude? Others only Asmita and Prerna, they are telling understood. Others are not understanding. So, shall I conclude or not? Others, yes, sir, conclude. Asmita, you are telling, okay, Prerna, but others, please. Girls, boys side, anybody? Other girls, boys? Abhijit, okay, understood, conclude. Thank you, Abhijit. At least, okay. Arjun Ingre, thank you, understood and conclude. Abhijit is also okay. Thank you, then. So, now I request you to join. I will provide 1 second link because